طيب بسم الله الرحمن الرحيم. So last time we started to talk about distant vector algorithms, and we talked about Bellman-Ford equation. The main issue with the distant vector algorithms in general is the issue of the partial view. So routers do not have a global view at all. So so a router knows the cost for these directly connected links. However, in order to reach to any destination X far away, then it relies mainly on the distances that it receives from other neighboring routers. And this is the main issue, and we'll see that by examples today. So this router has to rely on the distances that it receives from neighboring routers in order to apply this Bellman-Ford equation to know the total distance to X, okay? So the equation itself is very easy, and it has to be applied in a decentralized way. So when I receive vector of distances from the neighboring nodes, I can always reach to that destination based on going to one of the neighboring links, which I know the cost for, plus the distance between my neighbor and the final destination. And that's the tricky part, okay? So we'll see that by example today. So from this simple example, so node U wants to reach to Z. So if node U wants to reach to Z, then what node U has is the cost for all the directly connected links, which is the cost for this link, the cost for this link, and the cost for this link. And what node U also has is the distance from the neighboring nodes, V, X, and W. These are neighboring nodes because I have direct connections to these nodes, okay? So node U at time t, okay, receives vector of distances from node Z, to destination Z from node V, and from node X and from node W, okay? V, X, and W, okay? So these are the neighboring nodes. So node U applies Bellman-Ford equation and say, okay, so if I need to reach to node Z, Maya? Anything that's not clear? So if node U wants to reach to node Z, then it knows that it needs to reach to node Z through one of the directly connected links. I know physically the cost for these links at any point of time. I always know that in real time, okay? So either I reach to Z through V. If I reach to Z through V, then I need the distance from V to Z, right? And I receive that from V, right? So either I need to go through V, which means I need the distance from V to Z, or I go through X. I know the cost for this, but I need the distance between X and Z, or I go through W, and I need the distance from W to Z. These are the distances that I receive, and I have to trust it, okay? Even if they are wrong, I don't know. These are abstract distances that I receive from the neighboring nodes, and I have to rely on it. Okay, even if they are, if there is some intrusion and these distances are wrong for some reason, I have no way of verifying whether they are correct or not. I have no way to verify whether they are minimum or not. I don't know if they are minimum because they are reported from the neighboring nodes, and somehow I have to rely on it. Okay, so applying the Bellman-Ford is very easy. So I can I accumulate the costs based on these three choices, based on the three neighboring nodes, and I select the minimum. So the minimum here is 3, and that's through node X. Okay. So then I put in the routing table at this point of time that to reach to Z, I have to go to the next hop through this port to go to X. That's what I know. Then it goes to X, and X will have to apply its own partial view to do this, to do the same forwarding process, and so on and so forth. Okay? So that's the A. Any questions?
No, yes. I'm just trying to follow and get out to solve those numbers.
Follow A? Follow what?
The step الأخيرة.
This one?
أيوة.
Right. So it's CUV, which is 2, plus the distance between V and Z. Distance between V and Z is here. So 2 plus 5, right? Okay? Or UX is 1 plus from X to Z. X to Z is 3, and so on. Okay? And then for all the neighboring nodes, I have to take all the choices and see which one is the minimum. Very simple. Okay? So once I reach to the minimum, I put that in the routing table. If it's different, so every now and then we receive these vector of distances and we calculate using the Bellman Ford. If something changes based on what I have in the routing table, then I have to update the routing table. If the routing table gets updated, this means that I need to inform others because I have new news now. I have some news, so I have to inform others. If the routing table does not change, then now I have the choice, okay? Because I don't have any news, okay? So either I have to report periodically, or if we are, why do I have to report periodically, even if nothing is changing? Because I don't know if there is a link goes down, link goes up, router goes down, router goes up. So I always have to regularly inform. Other distant vector routing protocols, they say, okay, so the probability of failure is low, and I can then trigger an event to send updates. So instead of proactively using periodic updates, then they say, okay, so we'll do this periodic updates for some time, but after some time, after a very long time, I can switch off the periodic updates and then report the updates only if there are some events. Okay? So that depends. We'll talk about this in the routing protocols. But this Bellman Ford is very straightforward. It's not like a complicated algorithm like Dijkstra. This is very easy. It's just one equation. So, so that's the explanation that's written here. So the basic idea is that for each node, from time to time, and this is underlined, from time to time, يعني how frequent, so that from time to time is a fluffy word, and it's by design, because some distant routing protocols, some distant vector routing protocols, they use periodic updates regardless. So like RIP is the oldest distant vector routing protocol, so it uses out updates every 30 seconds, regardless. It's very simple, okay? So we'll do periodic updates every 30 seconds. So why every 30 seconds? Why don't we stop? Because the idea at that time was that I don't know when I will reach convergence, because I have partial view. So it's better for me to just keep periodic updates. Some other distant vector routing protocols like EIGRP, of course we studied these before in Network 1 and Network 2. But EIGRP مثلا says, okay, so we'll do periodic updates, but after some time we'll stop the periodic updates and we'll rely on trigger-based updates. So we'll do every 30 seconds, but at some point we'll stop this and we'll rely on trigger-based updates, okay? Just to try to be more efficient. So, so every now and then I receive vector of distances from the neighboring nodes, and I have to trust them. When router X receives the new distant vectors estimate, صح? Because we don't know whether these are correct estimates, whether these are minimum distances. We don't know, okay? And we apply the Bellman Ford equation. And under minor natural conditions, the estimate conversions to the actual. Hopefully, this will lead to the actual minimum. When the distance is minimum, when the distance vector I receive from the neighboring node is minimum. Okay. So we have to keep updating each other until sometime, hopefully, we will reach convergence. And the state of convergence, by the way, in these types of iterative algorithms is hard to detect, because the state of convergence happens when all the routers have no change at all. Okay? So that condition, again, requires some global coordination. صح? يعني I need to have reassurance from all the routers that none of these routers have any single change to report. So that also requires a global coordination between the routers. So the state of convergence in distant vector routing protocols is usually very tricky to detect.
When you're talking, you're always like giving some relative.
Yes, relative distances.
Relative way of looking at things. But this relative way of looking at things also implies that generalization is difficult.
Yes. Yeah, again, I mean, here partial view is very limited. We cannot generalize, we cannot decide at any point of time that there is a state of conversion. Based on what?
Yeah.
We don't know. Okay, that's why we have to keep updating it periodically. So the good news is that it's an iterative and asynchronous. Asynchronous here is a good feature. Why? Because I don't have to synchronize these updates in any way. I don't have, a node doesn't have to wait for all the updates to come from the neighboring nodes. A node can decide to apply the Bellman-Ford equation at any point of time. If it receives one update, if it receives all the updates from the neighboring nodes, two nodes send update. Whenever it decides to calculate the Bellman-Ford, it can perform that, and there is a guarantee that we will always improve. In other ways, that using Bellman-Ford equation, it can never lead to diversion. And by diversion here, I mean what? That we try to iteratively go towards the minimum cost, and then at some point, because of any event, we go up again. So we'll go in terms of oscillation. This can never happen using Bellman-Ford equation, because simply the minimum cost is calculated through a linear function, and linear function is always convex, and it always leads to improvement. It can never lead to divergence. Okay, so that can easily be estimated. So each local iteration caused by local cost change. So if a node finds that one of the costs to any destination changes, this means that I have to report this in the routing table. Anything I report in the routing table, I have to inform all the neighboring nodes. Okay. So it's distributed, which we know that. Each node notifies neighbors only when its distant of vector changes are happening. Again, only if based on the routing protocol. Some routing protocols, they don't do that only if. They keep sending. Even if they don't have a change, they have to keep reporting that periodically. Rep does that, for example. Okay? So the algorithm, the algorithm itself is very simple. Wait for change from the neighboring nodes, recompute the estimates, which means calculate the distances, your local distances, based on the distances reported from neighbors. If there is any change, then you report it to others. And we keep doing this in a loop. So, of course, as we can imagine, the example is very simple. Again, it needs some practice just to make sure that you're not doing mistakes in calculation. But it's very systematic. Any node like X, so this is the table in X. X maintains what? X maintains its own partial view. Its own partial view contains what? Contains the coast to the neighboring nodes and contains the distances that are reported from the neighboring nodes to any destination, okay? So X has, of course, the coast to itself, which is 0. It has the coast to Y, which is 2. And it has the coast to Z, which is 7. That's what it knows. Of course, this is not the minimum coast, as we know, as we can see, but that's what it knows. The direct coast to Z is 7. That's what it knows, okay? And it has no information at this point from Y or from Z. I did not receive anything from Y and from Z, okay? So this is the view at node Y. Node Y knows that the coast to X is 2, the coast to Z is 1, and the coast to itself, of course, is 0, okay? But it has no information. This is at time 0, so this is at time 0. So here, there is the time aspect here. This is at time 0, okay? So here, we're supposed to have iteration number 1, where each node now receives the distance, the distant vectors from other nodes, and then it tries to do the calculation locally, okay? And if there is any change, then we have to report it to others, and so on. So we keep doing that. And hopefully at some point we'll reach to the state of convergence, where the state of convergence happens if no router reports any change to what they have, okay? So at time 1, each of these nodes will have to receive the vector of distances. So node X receives this line and this row and this row, okay? And then it needs to calculate the coast to the destinations based on what it has. Of course, remember, if I have node W here, for example, node X at time t0 has what distance to W? It doesn't know. صح? So it will put it as infinity. I want to make this clear. Huh? So node X at time 0 has no distance to W, so it put it as infinity. So if it has no information about anything, it puts it by default as infinity. So here, if I calculate the distance, of course, the distance to itself is 0 and cannot change. But the distance here, let's calculate this distance. The distance to here is either the distance to Z is either this 7, which is what I have, okay, or the distance to Y plus, sorry, the coast to Y plus the distance that Y reports about Z, okay? So it's 2 plus 1. So is it 3 or is it 3 or 7? Of course it's 3. So now X will change the next hop in the routing table to Y to go to Z, and the cost will be 3. Because this changes, then I need to update the routing table, which means that in the next iteration, I have to report all this line to my neighboring nodes. ماشي? If something changes, then I need to report to all the neighboring nodes. Node Y will have to do the same, okay? So node Y will have to do the exact same thing. So node Y here does not change anything based on what it has, because it has already the minimum cost and nothing needs to be changed. So, and node Z will have to do the same. Node Z updates its distance to X, of course, okay? Similarly to node X, okay? Here, as you can see here, when I switch to this at time T2, okay, all these tables now have the minimum cost, and if you try to run Bellman-Ford equation on this, you will find that there is no change in all the routers. So this is the state of convergence. Of course, we have reached the state of convergence using 2 iterations because this is a very simple network composed of 3 nodes. Imagine that if you do this using مثلا hundreds of nodes. But if you apply the Bellman-Ford systematically, it works, okay? Even for fairly large topologies. ماشي كده؟ طيب. So now we need to check برضو ايه the implication of this partial view that we have. This is a very interesting example. This example and the next example are very interesting examples to show you the implication of having partial view. Okay? So at any point of time, node X and node Y, they realize that now we have changed from a wireless link to an Ethernet link. So wireless link used to have مثلا less bandwidth. So now with Ethernet we have larger bandwidth. So the cost A drops from 4 to 1. Okay? So who knows this information? This needs to be very clear. Who knows this information? Only the routers that are directly connected to this link. So node Y knows that. Node X knows that. Node Z does not initially know that. Okay? It will have to get notified by either node Y or node X. This is very, very important to keep in mind. Okay? So node Y now will have to detect, node Y knows the cost, that the cost for this link dropped from 4 to 1. Okay? But it needs to receive the vector of distances from Z and X. Okay? And based on that, it needs to keep calculating the new cost. So at time t0, this is very important. At time t0, node Y knows that the cost from Y to X is now 1. Okay? And node Y receives the distance from Z and from X. What is the distance that Z reports to Y about reaching to X?
5.
Who agrees with that?
It will send what it knows. It will not send the update.
صح. Okay? So node Z will report to Y that I have a distance to X which is 5. Okay? And this is actually through Y, yeah? Through Y. شوف, the interesting thing now is that I will report to Y that the distance to X is 5. حد مش عارف 5 جت ازاي؟ 5 is 1 plus 4, which is the old cost. That's what Z has, right? And it's actually to go through Y. Okay? طيب. So now, let's see the implication of this. There is a discrepancy now in the information. We know this. We know this because we have global view. Okay? But for the decentralized nodes to rectify this situation, they know nothing but applying Bellman-Ford, right? So at time t0, node Y will receive the distance from Z to X as 5. Okay? So node Y will say, let's see. I will apply Bellman-Ford. صح? At time t0, I will apply Bellman-Ford. So Bellman-Ford says that the distance from Y to X is the minimum of the cost from Y to X, okay? The cost from Y to X, which is direct, and I have reached to the destination right away, or the cost from Y to Z plus the distance between Z and X. صح كده؟ حد مش عارف دي جت ازاي؟ صح؟ ما these are the neighboring nodes, صح؟ From Y to X, X happens to be a neighbor, but who knows? Maybe if I go to Z, I can reach to X through a minimum cost. I don't know. صح؟ صح كده؟ Okay. So that will be the minimum of what this cost is now 1, huh? Y knows that in real time. So this is an immediate information. I know that. I know that the cost for this link dropped from 4 to 1. That I know. Okay? Because this is based on physical ports. Huh? I get notified right away. Or the cost from Y to Z, which is 1 plus the cost from Z to X, which is 5. صح؟ وانت لسه قايل 5. Okay. So so the cost will be 1. Okay. So now the Y now has a new distance to X. صح? It used to be 4 and now it's 1. Okay? So then Y has to report this new distance to Z. So the Z will have to calculate its distance to X. And Z will realize that it will also have to go to Y. But now, because of the fact that the distance from Y to X is 1, its distance, the new distance to X is now 2. Okay? So in 2 iterations, we have reached the convergence. And that's what this message is trying to tell you, is that good news travel fast. So if the link costs improve, we converge fast. ماشي? That's good. So in 2 iterations, we were able to rectify the implication of that change. Let's see the bad news. Okay, let's see the bad news. Okay, again, Y will receive these distances at time 0. We'll receive the distance from Z, which is 5. Okay, although now the cost from Y to X is 60. Okay, and we'll receive from X, which is 60 برضو. Okay, so this is what we have at this point. So let's apply the same thing. Let's try to apply the same thing. So now Y will try to calculate its distance to X. So this is again the minimum of the cost from Y to X, or the cost from Y to Z plus the distance from Z to X. Okay? So this is the minimum of 60, or the minimum of Y plus 1 plus 5. صح? This is what I have. This is what Z tells me. Its distance to X is 5. So, sorry, 5. So the new cost is 6. So Y now will have a new cost to X, which is 6, and it's through Z. Okay? Although the distance reported from Z to Y is also through Y. So it's as if it's a fireball and everyone is trying to throw to the other one. Again, this is because of the implication of the partial view. Okay? Type. This is at time T0. Okay? Because this cost changes, now I have to report. Type. At time T1, dZx at Z بقى, Z will receive this from Y. Okay? So Z will say, oh, okay. So I can calculate the minimum distance to X. It's either 50, okay, or it's 1 plus 6. Oh, okay, it's 7. تمام? Okay, so note Z says, oh, okay, so the cost changes. Let me now report it to Y. شايفين البينج بونج effect? Okay? So this is a ping pong effect now. So we'll do this 44 iterations until, so we started from 6, which is 5 plus 1. We started from 6, okay? We'll go all the way to 50. Let's say when the distance from Z to X is 50. Let's see. So دايما يحصل لي البتاع ده. اوكي مش عايزين البتاع. Okay. So now طبعا after 44 iterations the distance to X reached 50. I will report it to Y. So Y will say the distance between me and X is either 60, which is a direct link, or 50 plus 1. Oh, okay, so it's 51. Okay, let me report that to Z. All of this happens in different time instances. The difference between these time instances can get as much as 30 seconds, as we will see in RIP. Okay? So now, dZx will be the minimum of 50, which is a direct link, or 51 plus 1. Okay. It's now larger. So now I have to go directly to X. That's a very crucial event now. So now I will switch the next hop from Y to X. Okay? That's when the convergence will start to happen. Okay? This is when the convergence starts to happen. Of course, the cost changes, but when I report this to Y, okay, the cost will stabilize. Why? Because Y will say, okay, so it's 50 plus 1, it's 51, and then we'll stop. خلاص. Okay? So this is the implication of bad news travels slow. Bad news travels slow. So what is the implication of this? Huge message updates, okay, that happened many times, صح? Until we have reached conversions. So message updates, everyone happens every 30 seconds. What is the implication on the data forwarding? Drastic implication on the data forwarding. Because Y will keep sending to Z to reach to X. And Z will do what? Will keep sending to Y to go to X. صح؟ So they will keep sending to each other. They will keep juggling So if Y receives data with a destination to go to X, Y will say, oh, okay, so the link that I have has a cost of 60, so I have to go to Z. Z will say, oh, okay, so I know the information I have is that my distance to X through Y is lower than 50. Okay, so let me send it to Y. So route updates, huge route updates unnecessarily, right? And even data loops. We'll have data loops. And this will continue for how long? Now we said 44 iterations at least. So each iteration happens every 30 seconds. So this will take minutes until we stabilize. During these tens of minutes, we have not reached conversions. Okay? So this phenomena is called count to infinity, which is also it's also covered in network 2. Network 2 we covered this. So there is a problem of count to infinity. So we'll keep juggling the packet to each other many times. Okay? To solve this problem, they have proposed a technique called a poisoned reverse. Poisoned reverse معناها ايه؟ If Z reaches to X through Y, it should not report its distance to x to y. Okay? In fact, it should report that its own distance to x is actually infinity. That's why it's called count to infinity. So this is the poison. So I'm trying to poison the update. So although z has some distance to x, but it's through y, which means that y owns this information. I should not inform y about this. واضح يعني is the concept clear? If I have the minimum distance to x through y, then y is the one that owns the information. I should not tell it the cost to x. I should tell y that the cost to x is infinity. Okay? This is the rule. It's called Poisson reverse rule. It's actually a rule. It's not an algorithm. But let's see how the simple rule will solve the problem. Okay? So instead of going through 44 iterations to reach to the state of convergence, let's see this Poisson update, how it solves the problem. Okay? So if z says that my distance to x is infinity and it reports that to y, okay? Then y will say, okay, so my distance to x is the minimum of 60, صح? Which is the direct link, or 1 plus a infinity. لا ما فيش 5 بقى ما هو the poison 1 plus the poison, okay? 1 plus infinity, okay? So it's 60. We know it's not 60. We know that. صح? But since the cost changed, I have to report that to z. Okay? So let me report that to z. So y will report to z that its distance to x is actually 60. So z will say, oh, okay, so my new distance to x is either 50 or 68 plus 1. صح? Following? So it's a. Remember, we have reached this last time in 44 iterations. صح? We have reached this in 44 iterations. Remember, when I did not confirm that the split horizon rule applies here. When y calculates the distance to x and estimates the distance to x is 60, this is through the direct link, صح? So applying the split horizon rule, the Poisson reverse rule, am I allowed to report the distance to z? Yes, because I'm not actually sending to x through z now. I'm sending to x directly. So I'm allowed to report that distance to z. Okay, z doesn't own that. I own it because it's directly connected. So when z receives that, it will realize that the new cost is 50 through x, not through y. صح? So am I allowed to report that distance to y? Yes. صح? Applying the Poisson rule, the Poisson reverse rule, z now sends to x directly, so I'm allowed to report to y. Okay? So y will receive the new distance from z to x, which is 50, and then y will say my new distance is either 60 or 50 plus 1, which is 51, and that's it. صح كده؟ So in 2-3 iterations we finished the why, because the concept is if I send to a destination through a node, this node owns that information. I should not tell it this information. I should actually give this information in a form of a poison, which is infinity. Okay, so it's like I'm poisoning the update. That's why it's called Poisson reverse. Okay, So the question is, will this completely solve the problem? The bad news is that it doesn't solve this problem 100% in all cases. So here, it did solve the problem because we're talking about a very simple topology of 3 nodes. Huh? Imagine that if we have hundreds of these nodes. So it doesn't solve the problem all the time. So there is still an issue with the count to infinity problem for large scale network. Right? So a quick comparison between link state and distant vector. In terms of the message complexity here, we mean the count of the messages that we need to send. So for link state, we know that the link states for all the edges needs to be reported to all the nodes. صح? So each node has to collect the link states for all the edges and send it to all the nodes in form of flooding. Okay? That's why the complexity for the number of messages is n, which is the number of nodes, times e, which is the number of edges. So all the link states for the edges have to be flooded in the network to reach to all the nodes. ماشي? So the complexity is n times e. Of course, this is the complexity in terms of number. Huh? The complexity in terms of communication cost is even more than this. Why? Because we have to use flooding. We have to use flooding means what? Flooding means that if we have a topology, complicated topology like this, then this node has to have all the link states for all the edges, and it has to send it to this router, and then this router will have to connect all the link states, all of them, and then forward to here, and then forward to here. It has to be flooded. هتقول لي ما هو اللينك ستيت بيعمل كده، سوري distant vector بيعمل كده. No, distant vector ما بيعملش كده. No, I receive only the distance of vectors from the neighboring nodes only. So I send it only for one hop. فاهمين الفرق؟ I send it for one hop only. But flooding means that every single link state will have to go propagate through the network. Propagate. ماشي? In a form of flooding. Every single link state. And every single router will have to collect a full link state database that contains the individual link states for all the edges in order to be able to apply Dijkstra and calculate the shortest path tree. Okay? In order for this to happen, I have to flood this throughout the whole network. ماشي? So in terms of communication cost, it's even more than this. ماشي? Now for links, for distant vector, I don't know, because it's an iterative algorithm, and we have to keep sending this periodically, and even if we send it trigger based, when we don't know when the state of convergence will happen, صح? So we'll have to keep sending. So we don't have a quantitative count of this number of messages. We cannot calculate the number of messages. It's not deterministic. It cannot be deterministically counted. ماشي? We have because of this partial view, and it has to be completely decentralized. So we have to keep sending these messages. ماشي? In terms of speed of conversions, as we discussed last time, the complexity of the Dijkstra algorithm is O of n squared. Why? Because we have to insert node by node into n dash, remember? This n dash, we have to report node by node, and every step we have to calculate n minus 1. So we said that we start with n minus 1 and then n minus 2, and then so we calculated the series to be a O of n squared. Type for distant vector, again, it's iterative. We don't know. We cannot actually, because we apply an equation, but we don't know how many times we apply this equation. صح? So we know the complexity of the equation for Bellman-Ford. It depends on the number of neighbors. So the number of neighbors depending on the topology. So again, we don't know We cannot count how many times we apply the Bellman-Ford equation. Okay? And this is the case, of course, for all the iterative algorithms. We don't have a quantifiable complexity, right? واضح كده؟ So if you run any iterative algorithm, ماشي? Sometimes it runs يعني fast, sometimes it gets slow depending on the parameters. So you never know a quantifiable number of times or number of calculations where this algorithm runs. طيب, another important feature بقى is what happens if a router malfunctions? A router malfunctions معناه ايه؟ A router will report a wrong cost about a link. So we need to know which type of algorithms will be more resistive to this type of error. ماشي? So imagine, يعني مثلا for the previous example, reporting the cost or a cost becoming 60, this was the wrong information actually. But the router picks that the cost is 60 even though it's 1. Okay? So in reality, it's actually 1. But it reported that it's 60 because of some malfunction or intrusion. Okay? So which of these techniques you think is more resistive? Is more resistive to these types of error or this type of malfunction for the router? So in that case, the distant vector is more resistive. Why? Because the distant vector will have to report the individual link states for all the edges independently. Okay? So one مثلا or two of these link states will be wrong. Just one will be wrong, صح? Because we have to maintain the link state database with all the individual link states. صح? If one router is malfunction, one of these edges will have wrong link state. صح? Just one, مثلا. معايا? What is the implication of this? There is an implication, of course, but I can argue that this implication will be localized because it's an error in one of the states of one of the edges will propagate to all the routers, صح? But the routers will deal with this as one independent wrong value. So the effect of this will be localized. Okay? And the implication might not be actually that big if you assume that if the cost here is high, the routers will try to avoid that link and will go through other links. So that will keep the network working. There's no issue. Okay? طيب. For distant vector بقى, we don't have link state database. Okay? If a router has malfunction and has reported one link with error, with the cost of error, this error will propagate and will affect the estimation of distances to all the neighboring nodes, صح? Which will in turn affect the estimation of distances in the following routers and so on and so forth. Which means that this error will propagate and cause an accumulation of errors to all the routers in the network. Why? Because the routers around me will rely on this wrong information to estimate their distances. صح? So their distances will be based on something that's wrong. So their distances will be wrong. صح? And these routers will report it to others. So others will have to rely on wrong information to estimate their own distances and so on. So the effect of this single error will propagate and will actually will accumulate. So the error for the distant vector will not have a localized effect. The error will propagate to the entire network and will affect the estimation of distances for all the routers. Okay? Do you agree? Okay? Why is everybody sleeping now? Calculations are hard to follow, I know, but yeah, it's not difficult, by the way, but yeah, it requires some practice. يعني. تمام كده؟ So غير كده احنا we have talked about this. We talked about for link state, node can advertise incorrect link cost. So we talked about this, and distant vector node can advertise incorrect path, and each node stable used by others will be in error, so the error will propagate. So this is the quick comparison between link state and distant vector routing protocols, particularly when it comes to incorrect cost on some of the edges. So we know now that link state routing protocols, they are more resistive to errors at least, okay, and they have to have global view. That might be an overhead. In terms of link state updates, remember, as we said last time, for link state algorithms, the link states for at the beginning, if this is T, the link states will be very, very high in the beginning to report all the link states for all the edges. Okay? Once all the routers have the link state database synchronized, so these link updates will drop, and will happen only if there is a change for one of the links. If there is a change for one of the link state for this particular link will have to propagate again, and will have to flood the network for this link only. That's why in terms of link state updates, it's very, very high at the beginning because we have to flood, but after a certain period of time, I don't have to report anything. However, for distant vector, as we said, it's periodic. Some routing protocols, they try to be more efficient, like EIGRP. REP is very primitive. EIGRP says, okay, so I will have to, after some time, I will still report periodically, but after some time, I will switch to triggered updates. So triggered updates reduces the overhead of sending these distant vectors. ماشي؟ طيب. Hierarchical routing is nothing but trying to limit the domain where we have to apply distant vector or link state. So as you can imagine, with the link state updates, will have to flood, صح? Do you imagine that these link state updates will have to flood the entire internet? So the entire internet will have to deal with continuous flooding of these route updates? Of course not. So there has to be like boundaries where these flooding or route updates will have to be confined within domains. ماشي? So the internet as an architecture is based on decentralized concept, right? So to maintain this, the Internet Engineering Task Force, they define what's called the administrative autonomy. Administrative autonomy defines the concept of autonomous system. An autonomous system is an infrastructure of a network which is owned by one administrative authority. Okay, so Ooredoo, مثلا, Ooredoo is an internet service provider. They have a confined domain of infrastructure, okay, where they are allowed to use any routing protocol inside that domain. ماشي? But the route updates, whether it's link state or distant vector, is confined within the domain of Ooredoo. So the internet is now divided logically into autonomous systems, okay? Within each autonomous system, I can apply anything, link state or distant vector, link state or distant vector, and sometimes both, by the way, okay? theoretically I can apply both. Okay? So, but the route updates will not go beyond that boundary, will not cross from one autonomous system to another autonomous system. Okay? So each autonomous system will have what we call border gateway. This border gateway is like a highway. So imagine each autonomous system is like a city, okay? And we connect these cities using highways. Okay? So the route updates, they do not go through this highway. Route updates or link states, they are not flooded, they cannot be sent through this highway. They don't cross the autonomous system. So they come at these boundary routers and they stop. So this way we will make the route updates or link state flooding, will make it scalable within a specific domain. Okay? So each autonomous system administrator will have full control within their domain. They can apply any kind of routing protocol internally. Okay? But these highways, they use different type, completely different type of routing protocol. حد فاكره؟ We studied this in network too. حد فاكره؟ It's called Border Gateway Protocol. ماشي؟ So Border Gateway Protocol is another type of routing protocol that's used to facilitate the interconnection between autonomous systems. ماشي كده؟ Each of these autonomous systems is under the control of one administrative authority. And then when we cross the highway, we go to another autonomous system. So if there is, if there is one final destination here, X, okay, this autonomous system could have direct connection to X or might have to go through this autonomous system to reach to X. So typically, if we want to communicate with someone in China, we definitely have to go outside of our autonomous system, which is currently مثلا controlled by Ooredoo or Vodafone. Okay? So we have to go to Ooredoo, and Ooredoo will have to go through another autonomous system, sometimes in Europe, okay, or maybe in the US, to go to China. That's what typically happens. So by doing this, we have to trigger by more than one type of routing protocol. We have to go internally through Dijkstra or through Bellman Ford. We use REP, we use ERGRP, we use OSPF, okay? And then when we go here, then we have to use a border gateway protocol to go from one autonomous system to another. So this way, we can align with the decentralized architecture of the internet, and we can decentralize the control. So this actually makes the internet scalable, but we need to have this hierarchical routing. Hierarchical routing talks about the fact that we have to use at least two levels of routing. One is interior, inside the autonomous system, and one is exterior, to facilitate the communication or the interconnection between the autonomous systems. ماشي كده؟ So inside the autonomous system, we know that the criteria is a shortest path, minimum cost. All the interior routing protocols, they call it intra autonomous system routing. Intra معناها inside. Intra يعني معناها within. Any routing protocol within the autonomous system, okay, uses the criteria of minimum cost path. Regardless of what cost is, this cost can be defined in different ways, but we use the minimum cost to reach to any destination. Okay? For border gateway protocol بقى, there is another factor which is more important compared to the shortest path. This factor is policies. Okay? يعني كمثال, I can reach to China through Europe or through the US. Okay? Which one is shortest? Probably to Europe. But the policy says I have to go through the US. So you go through the US. يعني معناه إيه? Policy in terms of in terms of service level agreement. I have an agreement with AT&T. I don't have an agreement مثلا with Orange in Europe. I don't have an agreement with Orange. I have an agreement with AT&T مثلا in the US. So in order to go to China, I'm restricted. I have to go to the US. Even I know that I can reach to China يعني faster through Europe, but the policy says I have to go through US. The policy now is more strict أو يعني has higher priority compared to the shortest path. So especially when I go from one autonomous system to another, the policy comes number one. If the policy says that I can reach to Orange or AT&T, okay, I can reach through both. Okay, so now I can use the shortest path. So that's the logic. ماشي كده؟ This is the concept in the hierarchical routing. So there is again the concept of autonomous system. So we know that the autonomous system is a group of routers in an infrastructure which is controlled by one single authority, one owner يعني. Okay? Routers in the same autonomous system, they run the same routing protocol. احنا we call it intra-autonomous system routing. Intra معناها within. ماشي? Intra means within the autonomous system. So you can run by Dijkstra, you can run يعني distant vector or link state, it doesn't matter. You have full control. And in fact, some organizations, they run both. Okay? And some organizations, they use different cost function for the same link. And they use different costs depending on the type of service. It's complicated, but يعني they have it. But theoretically, if you have two routing protocols running, so the routing table will be fed from both of them at the same time. Okay? So is that possible? Yes, it's possible. In many ways, it's possible. So there is, this is very important. We have a gateway router. We call it border gateway router. This gateway router needs to have border gateway routing protocol, okay, to interact with the other autonomous systems. And will also have the interior routing protocol, whether it's REP or OSPF, to report to the routers inside about all the link updates or something like this. It will have both. This border gateway protocol is very important. Sometimes some autonomous systems may have two border gateway protocols or border gateway routers. So this is how the autonomous systems look like. So you have autonomous system 1, 2, 3. So this is, let's say, this is مثلا AT&T, this is Ooredoo, this is Vodafone. Okay? So these routers now will have a routing table, a forwarding table, which gets fed from autonomous system routing algorithm, which is border gateway protocol, which is the one that controls these highways. These are the highways. These are highways. Okay? And we'll have the intra-autonomous system routing algorithm. Intra اللي هو ايه OSPF بقى REP and so on. This is the one that has the route updates inside the autonomous system. And both of them, they feed the routing table. So the routing table will have destination addresses and will have next hub. So at the end, this is what the routing entry will have. So this information can be fed from both of them at the same time. For example, if I have a destination inside the same autonomous system, chances are this information will come from interior routing protocol, like REP or OSPF. But this router should also know how to get to China. There is a destination which is very, very far away. right? So how would I get information or reachability information to this destination? It happens through, it goes through the highway until it reaches here through border gateway protocol. This border gateway protocol will also feed to this routing table saying that if you want to reach to node X, okay, so you have to go this way. You have to go to this next hop. So at the end of the day, the entry in the routing table is forwarding rule. If I need to go to this destination, I can just go to this next hop. That's it. Okay? So this gets reported from multiple routing protocols. It's possible. تمام كده؟ طيب. So now this is a fairly complicated scenario. We have multiple autonomous systems. So suppose router in AS1 here, like مثلا this 1D مثلا. This router receives data ground distant outside of autonomous system 1. This is what we have been discussing. So here مثلا, destination X مثلا. So the router should forward packet to the gateway router الأول. So should first route the packet to the border gateway router. And this border gateway router is the one that will have access to the highway. So we'll have to do it based on two phases. So the first phase might use the shortest path, using REP or Dijkstra or anything. But this border gateway protocol will have to use other rules. Could be policy, another factor, policy. It could also be shortest path, okay, until it reaches to the final destination. So A1, autonomous system 1 must learn which destination are reachable through AS2 and which destination are reachable through AS3. Could be both. يعني مثلا this destination X could be reachable from here or here. Okay? So if it's reachable from one autonomous system, that's easy. I will forward it to the border gateway, which is closer to this autonomous system, and off you go. That's it. I have no ambiguity. But if it's reachable from both, which is this example here. So this example here talks about the fact that if 1D wants to reach to X, and X is reachable only from autonomous system 3, so the information at the end that 1D will have in its routing table to reach to X is through this interface, which will go to A1 مثلا, will go to 1C, and then will go to the autonomous system 3. Lower gateway 1C will have to go through gateway 1C. From 1D to 1C, that's shortest path, normal. That's a normal shortest path, REP, ERGIP, whatever. And then the router 1C will have to use the highway. ماشي؟ طيب. This is a complicated example. So if router 1D wants to reach to X, it knows from the routing table that there is a reachability information through autonomous system 2 or autonomous system 3. ماشي? So which one it should choose?
Who knows exactly that who knows exactly that there's two options?
We know because we have the global view. We know that we have the global view. Systematically how would 1D know which autonomous system it should go through? Should it go through, send it to 1B in order to go through autonomous system 2 to reach X? Or should it go directly to 1C in order to reach to autonomous system 3 to X? This is the question now. Because if this link is not there, we have only one option. We don't have a choice. So we have to send it to 1C in order to reach to X. We know that. Okay? But unfortunately, in this example, it's fairly complicated. And that's typically what happens in the internet. ماشي؟ طيب. Here we have to apply logic. It's hierarchical routing, of course. We have to go through 2 levels of routing. We know this. So first, we apply the exterior routing rules, okay? Because first, we have to check the policy. Sometimes you have a policy based on the service level agreement. If you have a reachability information to a specific destination through Vodafone and Ooredoo, you have to send it through Ooredoo by default. That's a policy. It's a written policy. ماشي? So the policy supersedes anything. In that case, you don't actually apply shortest path. You have to go to the path that fulfills the policy. Okay? If you don't have such policy, then you apply the shortest path. Then, مثلا, if let's say, if the coast from 1D to 1B is 1, and the coast from 1D to 1C is 4, and you don't have a policy that says that, مثلا, for a destination in China, you have to go through autonomous system 3. If you have that, you will have to go through autonomous system 3, even if it's not the shortest path. But if you don't have this policy, then now you have the choice. Then you apply the shortest path within the autonomous system domain. So what is the shortest path? To 1B or to 1C? To 1B. So hopefully when it goes to 1B, it will go to autonomous system 2, not 3. So you will reach to X through shortest path. ماشي? So this is the interaction between the exterior routing protocol and interior routing protocol. So using this logic, we can have the hierarchical routing. So we call this hot potato routing. Hot potato routing here talks about the fact that you have a hot potato that it can be juggled to this autonomous system or this autonomous system. So which one should you go? Okay, because it's a hot potato, you will send it to the one with the shortest path in that case. But that's conditional to the fact that there is no policy that restricts the traffic to X to have to go through a specific autonomous system. That has to be clear. ماشي? So this is what this example tries to do. So learn. So first we will learn. Of course, we'll talk about by the route updates within the border gateway protocol. So learn from the inter-autonomous system protocol that subnet X is reachable via multiple gateways. So we get this through updates from border gateway protocol. We get route update from both gateway routers that they have a path to X. Okay? So in that case, we say that, okay, so first we apply the policy. The policy says it's okay. So in that case, we say, okay, so what is the cost to each border gateway router? And we select the one with the minimum cost. So use routing information from the intra-autonomous system protocol to determine cost, at least cost path to each border gateway router. And then we apply the hot potato routing, choose the gateway that has the smallest least cost, and then we forward it towards that border gateway router. ماشي? So this is called hot potato routing. Let's have 5-10 minutes. So until then, we have covered the 3 types of routing algorithms: link state and distant vector, and also hierarchical routing. Hierarchical routing is a hybrid, so it talks about 2 levels of routing where you can apply any interior routing protocol, but you have to apply a border gateway protocol. So now,
when we say autonomous systems, what do we mean?
Autonomous system is group of network device infrastructure which is controlled by a single authority. Okay. Yeah, so Ooredoo, they have their own infrastructure which is controlled by them. Yeah. So all the route updates and everything, it's within their domain. Yeah. But if they want to communicate with any destination outside their infrastructure, then they have to go to another autonomous system which is under the control of another authority. So in that case, they have to use border gateway protocol. So now we talk about the protocols, okay? So protocols here, they use one of the algorithms that we have talked about, okay? But with certain configuration, with certain parameters that we need to discuss. So REP مثلا, for example, is, so we have the intra-autonomous system routing protocols. So, or sometimes they call them interior. Interior means inside. Border gateway is an exterior routing protocol. So these are REP, OSPF, and IGRP, and we have EIGRP, of course. Okay, so EIGRP is the only one that's proprietary, but as far as I know, EIGRP has been standardized, maybe like 10 years ago. Okay, so we have REP, OSPF, and EIGRP. REP and EIGRP are examples for what type? Huh? REP and EIGRP or IGRP, these are examples for distant vector routing protocols. And OSPF uses a link state. Link state, huh? Yeah, link state. Okay, so OSPF uses link state. So OSPF has to go through by link state database, and we have to apply the extra and everything. But REP and EIGRP uses a Bellman for it. So we know that. So REP is the oldest one, of course. And it's very primitive. It actually relies on the fact that the cost for any link by default is 1. Okay? So if I want to reach from any node to any node, I count the number of hops only. Regardless whether I use wireless, I use Ethernet, I use point-to-point, whatever. The cost is by default 1. And it also uses a maximum number of hops, which is 15, which means that it cannot deal with very, very large infrastructure. So the maximum number of hops, عارفين hops يعني number of packet forwarding is 15.
So what will do?
The reason for this, the main reason for this 15 is that, remember the count to infinity? The count to infinity problem, so we have to use infinity. So infinity for the routing protocol is actually 16. For REP, it's actually 16. So if a node reports that the cost for its link has become 16, this means that it's disconnected. That it doesn't have any connection with this node. Okay? So it's like infinity. It's like totally disconnected.
What will the router do in this case?
It will have no connection to it. It will have to use border gateway protocol and so on. It has to forward it to the border gateway router, and the gateway router will have to go through the highway if there is any reachability أصلا. But within the autonomous system, it doesn't have any connection. Okay. So the distant metric is, as we said, is by default 1. Distant vectors exchanged with neighbors every 30 seconds. Okay? So every 30 seconds, we have to report distant vectors. There is no exception to this. We have to report periodically. That's it. EIGRP has an exception. As we said, after certain period of time, it will resort to triggered updates. Okay? So it starts with periodic updates, but after some time, it switches to triggered updates. ماشي? So it uses طبعا distant vector in terms of route advertisement. It calls it route advertisement. So each advertisement lists 25 destinations. So any router can report, which means that any router in the routing table, okay, reports 25 items in the routing table at any point of time. But what if there are more than 25 entries? That practically happens. Even for REP, it happens. In that case, you have to send multiple route advertisements. So 25 entries per message. ماشي? So we send the first 25 entries from the routing table in the message, and then we send the second 25, and then the third 25, and so on. ماشي؟ طيب. So for this particular example, if let's say router D needs to reach to any of these nodes, then as we see that so router D knows that to reach to destination W, where is W? Here. So router D can reach to destination W through two hubs, 1, 2. So router D can reach to destination Y, again through two hubs. Router D goes to destination Z through 1, 2, 3, and then until it reaches to Z, it's 7. So these are simply number of hubs. That's it. So the coast by default, I don't have to have a coast on each link because it's by default, it's 1. Okay? Now, router D receives distant vectors from its neighboring nodes. So it received from A that now A has a coast to Z, which is 4. So it receives from A that the coast has become a 4 to reach to Z. So this is received from router A. So router A reported its own distance to router D, which contains the fact that to reach to router Z, I can reach to router Z using 4, coast of 4 hubs only. How does this happen? So router A happens to have indirect link to Z, which currently it has become available. ماشي? So in that case, router D will say, okay, is it 7 or 4 plus 1? So now it's 5, 4 plus 1. So this way I can report the distances, and I can apply Bellman-Ford as we have done before. So now router A, remember, router A can report this coast through C. So the Poisson reverse rule applies. Okay? So A can reach to Z through C, ماشي? Not through D, so I can report that coast to D. The Poisson reverse rule applies here, so I can report to D that my coast to Z is now 4, and it's through C. ماشي كده؟ So link ferial recovery. So if I don't receive route updates from the neighboring node, okay, for a long time, which means that this link has become disconnected for some reason. How would I detect this? If I don't receive a route advertisement from a particular link for 6 periods in a row, okay, because we report every 30 seconds, okay? So after 180 seconds, which means 6 periods in a row, then I report that this neighbor is not a neighbor anymore. It's totally disconnected. Very easy. Okay, so that's also a row. So routes inside via this neighbor has become invalidated, and we have to use طبعا the Poisson reverse as we said before, used to prevent the ping-pong loops as we have discussed before. And the Poisson in that case is 16. So we don't use the infinity, we use a 16, because 16 for rep is actually infinity, because the maximum number of hops is actually 15. طيب. So here, rep routing tables managed by application level. The interesting thing here is that route updates or route advertisements, okay, these are control messages. It's sent from routers, right? So these messages, like any other messages, like data messages, they have to use protocol. They have to use a protocol data unit, which means it has to use a protocol header, right? So route updates, they use UDP for link advertisement. So each router sends route advertisement by encapsulating the 25 items from the routing table in a UDP over IP طبعا. In a UDP message over IP, and it sends it to the neighboring routers. So why UDP and not TCP? That's ليه بقى؟ حد عارف؟ إيه؟
Because of the need of acknowledgement.
برافو عليك. Because we by default we have to make it unreliable. Why? Because if we use TCP, TCP requires acknowledgement, okay? And the reason for this is that in many cases these route updates are sent using multicast. We can send it to both or all the neighbors at the same time. So it's called one hub multicast. So we send a message to all the neighbors. Okay? So if we have to wait for all the acknowledgement from all the neighbors, so we'll have to wait for a long time. And what if we receive acknowledgement from one neighbor and not the other? TCP will not work in this case because it relies on a 100% reliability. So we have to have acknowledgement from all the routers. And this will be very restrictive. So that's why the choice for UDP is to use, the choice for REP was to use UDP as unreliable transport protocol. EIGRP, by the way, uses IP directly. Because IP actually is unreliable. It encapsulates the messages directly to IP. But in that case, EIGRP doesn't deal with the port. Remember, because UDP uses port number. Okay? So in that case, EIGRP doesn't deal with port, which means that there's only one process. We don't have to feed the route messages to multiple processes in the router. So it's only one process, which is the EIGRP message advertisement. But in all cases, it has to be, or it needs to be unreliable. So the only exception to this is border gateway protocol, because it deals with highway point-to-point. So there are some TCP sessions that gets established between two autonomous systems. So that needs to be reliable, okay? And it needs to be also secure. So they use TCP and they use security layer on top of it as well. ماشي? But for REP, it uses UDP directly. كويس كده؟ So it uses UDP over IP, and then it sends the route advertisement using this protocol stack. طيب OSPF stands for Open Shortest Path First. Open here معناها publicly available. It's actually a redundant name because all these are standardized and it's supposed to be publicly available. It uses طبعا link state algorithm, which means that all the routers in that case, they will have to exchange link states, and all of them, they have to maintain link state database that has all the link states, individual link states for all the edges in the network. OSPF advertisement carries one entry per neighboring router, and this entry gets flooded, as we said, okay? So the link state will have to flood, as is كده, will have to flood through all the routers. It doesn't get summarized or aggregated or something like that. It has to be sent to all the routers in a flooding fashion. Okay? طيب. So advertisement disseminated to entire, this is very important, Again, these route advertisement, they have to be blocked by the border gateway routers. They don't go across the other autonomous systems. It's very important. So they have to be confined within the autonomous system domain. So the messages are carried, as we said, over IP directly. EIGRP and OSPF, they both use a IP directly. So there's no port. They don't deal with ports. So OSPF بقى has advanced features compared to REP. In addition to the fact that it's link state and it deals with link state database, it uses also security. So all SPF messages have to be authenticated. So routers, when they send route advertisement, before that they have to authenticate the router. So we know authentication, of course. So we have to have authentication with the router before we accept any route advertisement. That's a very important feature in OSPF. So multiple same course paths are allowed in OSPF. So imagine if any of the examples that we talked about before, that a router receives from neighboring node, okay, the distance to a particular destination. So any router receives from router X and router Y the distance to destination Z. So both routers says that our destination to Z is 10. Okay, so which one I should choose? Should I go through router X or should I go to router Y? Okay, in that case, rep selects any one of them randomly. Okay, so any router now has a destination Z, and it has two routers. This is router X and router Y, and router X and router Y, they report the same destination to Z. Let's say it's 10. Okay, and here, let's say this is 2 and this is 2. Okay? So rep deals with this situation that, okay, so I'm going to keep only one route in the routing table. I will select one of them, I will keep it in the routing table. OSPF, interestingly speaking, it will keep both. OSPF will say, no, in the routing table, I can say I can reach to destination Z using X and Y. And it will keep both entries in the routing table. Why that?
One fails, has the other. One fails, has the other.
Okay, so that's one good reason. Okay, so one will be backup to the other. The other interesting scenario is that I'm keeping both of them, and in case of and for routing, I will route through both actually. I use the concept of load balancing. Okay, so if I have a packet that comes here with a destination Z, one time I will send it through X, one time I'll send it through Y. So this will balance the load because it's the same cost. Okay? So it applies Dijkstra, and if Dijkstra says that the same cost from both, so I will keep both. And I will keep juggling the packets between both paths. So it uses load balancing until one of them becomes unavailable, it uses the other. ماشي? Another interesting feature in OSPF is that for each link, multiple cost matrix for different type of service. Okay, so I can use different metric costs for the same link. So if I have a link to X, this link might have a cost that is مثلا 10, but this 10 is for a real-time application. But I have a satellite communication that can reach me to X, okay, with a cost of, let's say, مثلا 5. But this 5 is for browsing. But for real-time application, this cost will be 100. Okay? Confusing enough? So it uses multiple cost matrix for the same link. And it uses the cost depending on the type of service. So if a person, مثلا, if a person is browsing the internet, I will force the traffic for that particular application for browsing to go through the satellite, because the person doesn't care whether it's delayed or not. So this is an implicit way of doing load balancing on the same link. But if that person wants to have a remote surgical operation, okay, then the cost for the satellite link will become 200, so that I can force these types of applications to go through the direct link to have faster traffic. So OSPF does that. So by the fact that OSPF maintains two paths or two coasts for the same link, you can apply these concepts of load balancing or having different routes for different types of service. OSPF has the ability to do this. ماشي كده؟ طيب. OSPF also deals with multicast much more efficiently compared to RIP. So here, we're talking about multicast in terms of data traffic. So we have what we call multicast OSPF. Because OSPF by default maintains route updates and stuff for one point to point, for unicast traffic. But multicast OSPF keeps route entries in the routing table for multicast. So it can, again, this is using the feature of having to send through 2 or 3 ports. So if you are trying to send to a multicast address, the packet will be forwarded through 3 ports or 2 ports. ماشي واضح كده؟ So I can send one packet to 2 ports or 3 ports at the same time. So this is multicast forwarding. Multicast is point to one point to many points. So I'm sending to group of destination, not just one destination. I'm sending to group of destinations. So I can send to both ports at the same time. Okay? So multicast OSPF is the extension of OSPF to deal with multicast sessions. And here, we're not talking about route updates here. Here, we're talking about data. Huh? We're talking about routing data. واضح? So, there is part of the concept of hierarchical OSPF. This is not hierarchical routing. Huh? This is hierarchical OSPF. So this is the last slide we go through. So hierarchical OSPF here deals with the fact that within the same autonomous system, this is one autonomous system. Huh? So within the same autonomous system, OSPF defines the concept of area. Huh? These are not autonomous, these are area. So it's an area inside the autonomous system. Okay? So OSPF uses a backbone area. This backbone area connects multiple sub-areas within the autonomous system. Why? Why do we deal with the concept of areas? Again, for controlling the flooding. To control the flooding. Okay? So the route advertisement will be flooded within the area only. So from one area to another, again, we use a concept similar to the hierarchical routing, but within the autonomous system, just to make OSPF more scalable to large infrastructure. REP doesn't have any of this, and that's why it's not really suitable for large infrastructure. But OSPF is very, very scalable. And until today, we use OSPF very, very commonly for intra-autonomous system routing. So the most common 2 routing protocols are OSPF and EIGRP at the moment. Those are the most common things. REP is يعني, relatively outdated. Nobody uses it, except if there is a small topology. So the OSPF deals with the concept of areas. So here we have area border router. The area border router acts as if it's like a border gateway router, but within the same autonomous system to facilitate the interaction between an area and the backbone. And this is the border gateway router that gets me outside of the autonomous system completely. واضح? So the border gateway router connected within the backbone which is connected to multiple areas. I can do the link state advertisement within an area, again, to control the overhead related to flooding the link states. Okay? So from one area to another, I have to go through area border router to the backbone and then to another area. I have to do this. This is the cost that I have to pay back. But this concept makes the OSPF much more scalable for large autonomous system infrastructure. واضح كده؟ Okay? So we need to know about this is backbone router. The backbone is just a designated area, okay, which is where the border gateway router is, and this backbone area connects with all the other areas within the autonomous system. Any questions? So this is the definition of each of these ones. So we have the area border routers, which summarizes the distance. The area border routers بقى will summarize طبعا within each autonomous system, يعني Ooredoo or Vodafone or any autonomous system will have a range of IPs. Remember that we have a range of IPs. Okay? So from one autonomous system to another, this range of IPs can be summarized. Remember we talked about route aggregation or route summarization. So the range of IPs can be summarized. Okay? So if I want to reach to a particular autonomous system, I have only one entry in the routing table which summarizes all the IPs in that autonomous system. Okay? Which will allow me to go to that autonomous system. So the backbone routers, they run OSPF routing limited to the backbone only. So the route advertisements or the link states within the backbone, again, they are confined within the backbone area. This is the link state advertisement. And then the border routers, they connect to other autonomous systems, and we have the area border routers, which summarize the range within one area to facilitate the communication with the other areas or the backbone area. ماشي? So that's the hierarchical concept within OSPF, which facilitated OSPF to be efficient and more scalable for large-scale infrastructure. ماشي.
Having a geographical area or يعني ولا هذا بس خاصة بالIS?
This ISP خاصة بالISP, yes. Here we're not necessarily talking about geographical area. So one autonomous system, by the way, could cover very large geographical area. يعني Ooredoo مثلا, they could have branches in Europe. They could have part of their infrastructure in Europe or Asia, okay? But all of these routers, they are under the control of Ooredoo. So it's not based on geographical area. It's based on the control authority. واضح كده? That's a good question. خلاص, we'll talk about this next time, inshallah.
Victor, do we find them يعني and companies